the renal tubule called the peritubula. Capillaries. A minute vessel of this network runs parallel to the hinglays, loop forming a U-shaped vasa recta. Vasa recta is absent or highly reduced in cortical nephrons. 16.2 Urine formation. Urine formation involves three main processes, namely glomerular filtration, reabsorption, and secretion, that takes place in different parts of the nephron. The first step in urine formation is the filtration of blood, which is carried out by the glomerulus and is called glomerular filtration. On an average, 1,100 to 1,200 milliliters of blood is filtered by the kidneys per minute, which constitute roughly 1/5 of the blood pumped out by each ventricle of the heart in a minute. The glomerular capillary blood pressure causes filtration of blood through three layers, i.e., the endothelium of glomerular blood vessels, the epithelium of Bowman's capsule, and a basement membrane between these two layers. The epithelial cells of Bowman's capsule, called podocytes, are arranged in an intricate manner so as to leave some minute spaces called filtration slits or slit pores. Blood is filtered so finely through these membranes that almost all the constituents of the plasma except the proteins pass on to the lumen of the Bowman's capsule. Therefore, it is considered as a process of ultrafiltration. Afferent arteriole. Efferent arteriole. Bowman's capsule. Proximal convoluted tubule. Figure 16.4 Malpighian body, renal corpuscle. Rationalized 2023-24. Excretory products and their elimination to 0.9. The amount of the filtrate formed by the kidneys per minute is called glomerular filtration rate, GFR. GFR in a healthy individual is approximately 125 milliliters per minute, i.e., 180 liters per day. The kidneys have built-in mechanisms for the regulation of glomerular filtration rate. One such efficient mechanism is carried out by juxtaglomerular apparatus, JGA. JGA is a special sensitive region formed by cellular modifications in the distal convoluted tubule and the afferent arteriole at the location of their contact. A fall in GFR can activate the JG cells to release renin, which can stimulate the glomerular blood flow and thereby the GFR back to normal. A comparison of the volume of the filtrate formed per day, 180 liters per day, with that of the urine released, 1.5 liters, suggests that nearly 99% of the filtrate has to be reabsorbed by the renal tubules. This process is called reabsorption. The tubular epithelial cells indifferent. Segments of nephron perform this either by active or passive mechanisms. For example, substances like glucose, amino acids, Na+, etc. in the filtrate are reabsorbed actively, whereas the nitrogenous wastes are absorbed by passive transport. Reabsorption of water also occurs passively in the initial segments of the nephron, figure 16.5. During urine formation, the tubular cells secrete substances like H+, K+, and ammonia into the filtrate. Tubular secretion is also an important step in urine formation as it helps in the maintenance of ionic and acid-base balance of body fluids. 16.3 Function of the tubules. Proximal convoluted tubule, PCT is lined by simple cuboidal brush border epithelium, which increases the surface area for reabsorption. Nearly all of the essential nutrients and 70 to 80% of electrolytes and water are reabsorbed by this segment. PCT also helps to maintain the pH and ionic balance of the body fluids by selective secretion of hydrogen ions and ammonia into the filtrate and by absorption of HCO3 from it. Henle's loop, reabsorption is minimum in its ascending limb. However, this region plays a significant role in the maintenance of high osmolarity of medullary interstitial fluid. The descending limb of loop of Henle is permeable to water but almost impermeable to electrolytes. This concentrates the filtrate as it moves down. The ascending limb is impermeable to water but allows transport of electrolytes actively or passively. Therefore, as the concentrated filtrate pass upward, it gets diluted due to the passage of electrolytes to the medullary fluid. Distal convoluted tubule, DCT conditional reabsorption of Na+ and water takes place in this segment. DCT is also capable of reabsorption of HCO3 and selective secretion of hydrogen and potassium ions and NH3 to maintain the pH and sodium-potassium balance in blood. Rationalized 2023-24. Biology. Collecting duct. This long duct extends from the cortex of the kidney to the inner parts of the medulla. Large amounts of water could be reabsorbed from this region to produce a concentrated urine. This segment allows passage of small amounts of urea into the medullary interstitium to keep up the osmolarity. It also plays a role in the maintenance of pH and ionic balance of blood by the selective secretion of H+ and K+ ions, figure 16.5. 16.4 Mechanism of concentration of the filtrate. Mammals have the ability to produce a concentrated urine. The Henle's loop and vasa recta play a significant role in this. The flow of filtrate in the two limbs of Henle's loop is in opposite directions and thus forms a countercurrent. The flow of blood through the two limbs of vasa recta is Figure 16.5 Reabsorption and secretion of major substances at different parts of the nephron. Arrows indicate direction of movement of materials. Rationalized 2023-24. Excretory products and their elimination to 11. Also in a countercurrent pattern. The proximity between the Henle's loop and vasa recta, as well as the countercurrent in them help in maintaining an increasing osmolarity towards the inner medullary interstitium, i.e. from 300 mosmol, 1 in the cortex to about 1200 mosmol, 1 in the inner medulla. This gradient is mainly caused by NaCl and urea. NaCl is transported by the ascending limb of Henle's loop which is exchanged with the descending limb of vasa recta. NaCl is returned to the interstitium by the ascending portion of vasa recta. Similarly, small amounts of urea enter the thin segment of the ascending limb of Henle's loop which is transported back to the interstitium by the collecting tubule. The above described transport of substances facilitated by the special arrangement of Henle's loop and vasa recta is called the countercurrent mechanism, figure 16.6. This mechanism helps to maintain a concentration gradient. Figure 16.6 Diagrammatic representation of a nephron and vasa recta showing countercurrent mechanisms. Rationalized 2023-24. 212 Biology. 0.6. This in the medullary interstitium. Presence of such interstitial gradient helps in an easy passage of water from the collecting tubule, thereby concentrating the filtrate, urine. Human kidneys can produce urine nearly 4 times concentrated than the initial filtrate form. 16.5 Regulation of kidney function. The functioning of the kidneys is efficiently monitored and regulated by hormonal feedback mechanisms involving the hypothalamus, JGA, and to a certain extent, the heart. Osmoreceptors in the body are activated by changes in blood volume, body fluid volume, and ionic concentration. An excessive loss of fluid from the body can activate these receptors, which stimulate the hypothalamus to release antidiuretic hormone, ADH, or vasopressin from the neurohypophysis. ADH facilitates water reabsorption from latter parts of the tubule, thereby preventing diuresis. An increase in body fluid volume can switch off the osmoreceptors and suppress the ADH release to complete the feedback. ADH can also affect the kidney function by its constrictory effects on blood vessels. This causes an increase in blood pressure. An increase in blood pressure can increase the glomerular blood flow and thereby the GFR. The JJ plays a complex regulatory role. A fall in glomerular blood flow. Glomerular blood pressure GFR can activate the JG cells to release renin, which converts angiotensinogen in blood to angiotensin I and further to angiotensin II. Angiotensin II, being a powerful vasoconstrictor, increases the glomerular blood pressure and thereby GFR. Angiotensin II also activates the adrenal cortex to release aldosterone. Aldosterone causes reabsorption of NA+ and water from the distal parts of the tubule.